A capacitor consists of two parallel metal plates separated by air at a variable distance apart. Okay, so you can make this closer or further apart. Capacitance is inversely proportional to X. This is a very important clue. Oh my goodness. The capacitor is charged by a supply so that there's a potential difference between the plates. It's kind of like you connect this up to a battery. Battery. Or power supply, sure. Let's do power supply. And then there'll be a potential difference between the plates. So we need to say in terms of C and V for the charge on one of the plates and for the energy stored in the capacitor. So these are equations we kind of have to memorize. If we don't memorize, we can't really start with it. But Q equals to CV, the first one. And the other one, there's a few equations we can use, I guess. But one of it is half CV square. Alternately, I guess you could say half QV as well. But since they asked for C in terms of C and V, so we gotta stick with the original C and V. Okay, so this one we just gotta add it to your equation sheet, stick it on your bathroom wall. Then you remember, oh, that one is correct, okay. So now we see part B, there's something that's changed. The charge capacitor is now disconnected from the supply. Now that makes things a little bit strange now. Because previously, we charge here, right? So all the charges are kind of parked here. We got a lot of positive charge, positive charge, positive charge, positive charge, positive, and a lot of negative, 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 negative. But now we don't connect it to the circuit anymore. It's just there. The charges are there. And then we make them closer together. Move them closer. State in terms of C, V, L, and D, the new capacitance. How does separation distance affect this capacitance? There's a clue right here, right in the beginning. C is inversely proportional to X. That's why I highlight it. It's a very important clue. So we need to say here that, oh, they tell us that C is inversely proportional to X. So what that means is I can say, so Cx is a constant. These two can change in proportion to each other, inversely proportional. Which means, just now the original old one, let's call Cx, equals to constant, equals to the new C and the new X. Why got Cn? Because that's what they want, Cn. So I can say C times the old separation. What is the old separation? It's called X. Oh, sure, okay. We'll just call it X. Equals to new one, we'll just keep it as Cn. But the new separation, this is Xn. We need it in terms of L and D. So we're going to say that is L minus D. So Cn in this case will be Cx? Wait, CL. My bad. Originally is L. We cannot have X. I was like, wait a second, something is missing. Yeah, original length is L. This is the Ori X. Okay, so this is L. So CL equals to Cn, L minus D. So Cn will be CL over L minus D. Oops. Okay, so we can write here CL over L minus D. This is a very weird way of asking of these capacitor questions. Very rare too. Hardly see questions like this. Rare cookie. Okay, 1 mark. B1 for this. Next. Find the new charge on one of the plates. Is there a new charge though? Is there? Well, the question is, when your charges are already parked at the plates, negative is on one side, positive is on another side, and it's disconnected, the charges cannot go anywhere. They cannot escape. They cannot run away. They cannot go home. So they're stuck there. So the new charge is actually the same as the old charge. The charge did not change. No matter you put closer or further, the charge is still stuck on the plates. And the old charge, Q equals to CV. No Cn or anything. So we can just say, oh, this is just CV. And that's it. But you may say, Miss, I'm not convinced. I want to do the working. Okay, but we don't know this. We don't know the new C. We do know new C. We don't know the new V yet. Cn, if you manage to prove it just now, this is Cl over L minus D, correct? But Vn, we don't know yet. Oh, that's coming in the next part. So we cannot use this method because we don't have enough information yet at this stage of the question. And we cannot assume that the potential difference is the same. So let's go to part 3. Part 3. Find the new potential difference between the plate. Now, when you bring plates closer together, their potential difference change if they are disconnected. Oh my goodness. So here we can say new PD. Now let's go back to Q equals to C V. But now we want to find V first. So Qn over Cn. Qn will be, let's take the, in terms of C and V, the original, over Cn, which is Cl over L minus D. And this will give us, oh man, Cv times L minus D over Cl. C and C cancel out. So that leaves me with V times L minus D over L. So in terms of the old, what you call this, the old voltage, new voltage is something else. It's a little bit different. Okay, so one of these, each of these is 1 mark. Okay, last part. Explain whether the reduction or reducing the separation of the plates results in an increase or decrease in energy stored in the capacitor. There are a few ways to do this. One is thinking about the theoretical physical method. The other one is looking at some equations to kind of guess your way through. Let's look at the equations and then we'll look at the theoretical method. So energy has many equations, right? You can do E equals to half CV square. E equals to half, okay, let's give it some more space a bit. E equals to half QV. And the last one, E equals to half. See, if I sub away V, I should get Q square over C. Yeah. We want to ask, how does energy change? So capacitance is proportional to separation. That's what they told us. And if you are reducing the separation, we say that X is reduced, so capacitance increases. So that the first change we know is capacitance will increase. Capacitance will increase. Now the first case, how will voltage change? If we don't really know, we cannot say. We don't know how. Well, you can think of it like, okay, Q equals to CV. The charge on the plate is not going to change because it's disconnected. But C is increasing. So by right, V must decrease. But then they may not. See this one increase, one decrease. Does that mean E is constant? We don't know. There's a square here. They may not increase in the same proportion. You cannot say, oh, this one increase 2 times, decrease 2 times. Cannot. So we'll put this as question mark. We don't know how. We know the V will decrease, but we don't know how E will change. Let's look at QV. Q is constant. Voltage or potential difference across the capacitor will decrease based on this. So voltage will decrease, energy will decrease. Oh, very easy this one. Only got 2 things changing. Okay, let's check if the third one agrees. So third one says E is half Q square over C. Q is constant, it's not going to change. So if C increase, that's inversely proportional, means energy will decrease. So I have 2 equations confirming with me that energy will decrease. So I'm going to say energy will decrease. So energy stored will decrease. If I want to explain in terms of equation, I guess I could say because capacitance increases. I'm looking at number 3 here. I really like this one because there's more constant. Increases. So based on E equals to half Q square over C, energy will decrease. I just said the same thing. I just say the same thing twice. Never mind. Let's say again. Equals, so energy decreases. Okay. Energy stored will decrease is 1 mark. This one is not exactly in the mark scheme, but you can use the equation, I guess, also. 1 more mark here. Not 1 mark. All the same mark only lah, okay? One mark for reasoning and your answer. The other method, which the mark scheme uses, and also is a little bit more on the physical side, is to say energy will decrease because the plates attract. Now, wait a second. Let me explain to you first. Imagine this is planet Earth and you are standing here. You have an object on the table. How do you increase the GPE of this object? Think about it. You want to store energy in this object, gravitational potential energy. What you do is, you just take this far, far away, high up, and ta-da, you have stored GPE in the object. You store GPE by moving and putting an object very high up. Now, the moment you let go, this object is going to drop back to the ground because it is attracted thanks to what we call Fg, or weight, to the ground, or rather to the earth. Similarly here, plates, if you allow me to put them sideways, they have negative charge and they have positive charge. Now, it is not connected to a battery or anything, so it's isolated by itself. So if you have positive charge, they are attracted to each other. So if you want to increase the energy, what you do is you move this further away. You increase electric potential energy. You are storing energy in the field itself. Similar to this all. Okay, this one, you store energy by moving it further away and they are attracted. The moment you bring it closer together, in our case, we're reducing the separation of the plates, you're actually decreasing the energy. Like how, if you take the object on Earth and you put it nearer to the surface, it has lesser GPE. So if you take this positive plate and you move it closer to the negative plate, it has lesser in EPE. So let's write that down also. You bring this closer, you decrease EPE, stored in the field. This one also, you bring it closer, it's attracted already. So less decrease in GPE. That's what the mark scheme is talking about. So the other method is to say, because opposite charge plates attract, so energy decrease. So we'll write here, note, because oppositely charged plates attract. Okay, so to clarify, it's kind of very weird to have a disconnected capacitor, but you gotta know the difference of what is changing between a connected and disconnected capacitor. So I'm going to summarize down here as like a bonus revision session here. So firstly, let's look at a connected capacitor, which is what we are more used to. Connected capacitor. One example could be something like this. Connect to battery. So you will have plates that are charged, if it's fully charged. Okay, like this. And let's say we bring them closer together. We reduce the separation distance. Here are some facts. Number one, the V is constant because it's all connected to the battery. So when you have some potential difference across the plates, that is due to the EMF of the battery, and they're related, so that one is fixed because you're connected to the battery. Number two, the number of charges may change. Q equals to CV. V is constant. So if you bring the plates closer together, okay, remember we say C is proportional to 1 over X. Closer together means capacitance increase. C increase, Q will increase. As you bring them closer together, the charges are like, wow, I'm very attracted to the other plate. Let's put more people here. So they become a lot more charges here. So more charge will appear when you put them closer together and it's connected to a battery. So I'm going to write here, notes, observations. More charge gathers at plates because now they're closer together. Attracted to the other plate that is now closer. So based on this, you can say that energy increases. How do you check? Well, I think this time I will use E equals to half CV squared to check, because I know that V is constant. So if my capacitance increase, energy increase. That's for a connected capacitor. But what if you have a disconnected capacitor and you bring them closer together? So this is a possible case number 2. Now you have fully charged the plate, you disconnect it, and we don't draw the wire. Disconnect already, it's just 2 metal plates. You got the charges there. The charges are stuck there. They cannot go anywhere already. So the first observation I'm going to note is that the charge is constant. The amount of charge, which is Q, is constant. They have nowhere to go. There is no wire. Okay, so here you have positive Q on one side, and on the other side you have negative Q. So if I look at the equation, okay, and I say, alright, we want to bring the plates closer together, I know my capacitance is going to increase. Okay, based on our equation C proportional 1 over x, if I bring them closer, capacitance increase. So I look at QCV. Q is constant. Okay. C will increase as I bring them together, which means by definition, V must decrease if I bring them closer together. That's very strange. You bring closer together, the potential difference can change, Nani. Okay. And because of these two, we follow through the train of thought. Potential difference decrease. Okay, PD across the plate decreases. Okay, and lastly, we can talk about energy. Energy decreases. Energy stored is a better term. Decreases. So this one, I can use E equals to half Q squared over C, like what I did just now. Because Q, I know, is constant. If the C increase, energy have to decrease. So you look very carefully at the difference between these two. Whether the capacitor is connected versus disconnected, there's a slight difference in behavior. Okay, and if you still find like, Miss, I don't believe you, bring the capacitor closer together, the voltage will change one meh? Okay lah, we do get a simulation. Now, if I had lab equipment, I would show you in real life lah, but I don't. So here's a simulation. We got our separation plates. Okay, so we're gonna give it a charge. Alright, 1.5 volts. We got charge. We're gonna disconnect the battery now. Disconnect. Okay, now let's look at the voltmeter. Let's bring the voltmeter in. And let's connect one to the top plate. Actually, what's the separation? Oh, I can bring them closer. Okay, let's put them closer first. One to the top plate, one to the bottom plate. Now the voltage is 0.75. I'm going to move them apart. As I move them apart, you go from 0.75 to 1. It's getting bigger and bigger and bigger and bigger and bigger and bigger. 1.5 maximum. Wow. If I go closer together, the potential difference decreases. Large potential difference, small potential difference. That is the weird behavior of disconnected plates. If you're interested to know why, you gotta think about electric field resultant potential, which is another long video by itself. Maybe a bonus video someday. So this simulation, you can also check out the stored energy and how much charges are stored on the plates. So if I move the plates further apart, there's a lot of energy stored there. If I move the plates closer together, stored energy decreases because they are attracted to each other. Okay, so that's my external force, and the plate charge doesn't change. Now you say, Miss, wait, what if we connect the battery to it? How would this change? Well, let's try and see. So we have 1.5. Let's bring it further apart. It's still 1.5 volts on the voltmeter. Bring it closer. Still 1.5 volts on the voltmeter. It's not going to change. What is changing now? If you look at the graph on top, the plate charge is now changing. Little charge, even little charge. Wow, they're not very attracted if they're far away. Bring the plates closer together. Ooh, lots of charges appear on the plate. Now the energy will also change. Further away, less energy. Close together, lots of energy. Now this one is a different phenomenon compared to if it was disconnected from the battery. So this is disconnected, this is connected. Different phenomenon. Get this down in your notes as well. Okay, so I think that's all for today's video on capacitors. I'll see you in the next one.